Okay, so welcome to today's class. So today we'll be talking about sets. So these are the topics that we'll be looking at the sets. We will talk of the definition of sets, then we'll look at some types of sets. Then from there we'll talk about the subsets. Then from there we will look at the properties of the operations on the set. Then we'll try to identify some regions on the Venn diagram. That is when we have two sets and we have three sets. And then finally, we'll take a look at some practical problems involving sets. That is the two sets problems and the three sets problems. So without wasting much time, let us start the lesson. So when we talk of a set, it is a well-defined collection of objects. So for instance, let us have this over here. If we call the elements inside this container over here fruit, then just by the way we have defined it, we should be able to tell the kind of element we should have in this set over here. So for instance, realize that we have a banana over here, which is a fruit. We have an orange over there, which is a fruit. We have an apple over here, which is a fruit. We have purple over there, which is a fruit. And we have a grapes also over there. And these are all fruits. So by the way I have defined the set over here, it should tell me the elements that are supposed to be in the set and elements that are not supposed to be in the set. So for instance, if I have something like a cassava is not a fruit. So it means that we cannot add cassava to these elements over here. Another example, if for instance I have a mobile phone is not a fruit. So it means that if I am labeling this set over here, set of fruits, then I am not supposed to find a mobile phone in there. So all the elements that are contained inside this container over here are fruits. So that is what I mean by well-defined collection of objects. So we have defined the collection over there as fruits. So anything that is found in this set over here is supposed to be a fruit. Another example, I can define a set of animals. So in here, you realize that I have a bed, I have a dog, I have a cat. In here, I cannot have a banana because a banana is not an animal. I cannot have an orange in this set over here because an orange is not an animal. So by the way I have defined my set over here, that is animals, it should tell me the elements that I can have in there and elements that I cannot have in there. Another example will be the set of electronic gadgets. So when we talk of electronic gadgets, we are talking of the mobile phones, we are talking of the laptops, we are talking of the headset, the joysticks, the pen drive, the television set, and so on and so forth. So all these are electronic gadgets. So by the way I have defined the set over here, it should tell me the elements that I am supposed to have in this set and elements that I cannot have in this set. So it means that in here I cannot have something like a dog because a dog is not an electronic gadget. I cannot have a banana in this set over here because a banana is not an electronic gadget. So that is what we mean by the collection of well-defined objects. But in mathematics, usually we are interested in numbers. So let us look at an example of a set that involves numbers. So we can talk of the set of prime numbers. So when we talk of prime numbers, they are numbers with just two factors, that is 1 and themselves. So an example of that will be the number 2. An example of that will be the number 3. An example of that will be the number 11. An example of that is 19. Another example is 101. So all these are examples of prime numbers. So by the way I have defined my set over here, it should tell me the elements that I am supposed to have in there and elements that I cannot have in there. So for instance, we all know that 10 is a number, but we cannot have this number 10 in this set over here because we know that 10 is a composite number and not a prime number because it has more than 2 factors. So because of the way I have defined this set over here, it tells me that I cannot have 10 in that set. We can also talk of a set of integers. So when we talk of the set of integers, we are looking at the set of all positive and negative whole numbers and 0. I mean, 0 of course is a whole number. So the set of all positive and negative whole numbers. So we have 2, 0 as an integer. We have 2 as an integer. We have negative 2 as an integer. We have negative 10. We have 760. So you realize that because of the way I have defined this set over here, it tells me the elements that I can have in that set and the elements that I cannot have in that set. We can also take a look at the set of factors of 20. So you realize that because of the way we have defined this set over here, the set of factors of 20. So we realize that 1 is a factor of 20, 2 is a factor of 20, 4 is a factor of 20, 5 is a factor of 20, 10 is a factor of 20, and 20 itself is also a factor of 20. So because of the way we have defined the set, it tells us the elements that we can have in that set. So we cannot have a number like 7. We cannot have a number like 7 in here because of the way we have defined this set over here. So it means that 7 cannot be part of the factors of 20 because that is how we are defining the collection. So it means that if we come to this container over here, the only things that we are supposed to see are things or numbers that are factors of 20. But then we can also look at this over here, the set of beautiful girls. We cannot tell the elements that we are supposed to have in this set over here because beauty is something that to different people they define it in different ways. So someone might be beautiful to me, but to you the person might not be beautiful. People believe that beauty is supposed to be shown by a person's attitude, or people have other ways by which they define beauty. So if you ask for the set of maybe beautiful girls, maybe I might include someone like maybe Rahel. To me, maybe Rahel might be beautiful, but maybe to you, she is not beautiful. So it means that it fails to be well defined. So now it fails to be well defined. So now, because it fails to be well defined, we cannot have this thing over here as a set. Because when we talk of a set, it should be generally accepted. So wherever you go, everybody is going to testify to the fact that all these things over here are fruits, right? Everything over here is a fruit. Everybody is going to testify to the fact that everything over here is an animal. But if you want to talk of beautiful girls, then there are people who would challenge your opinion. So it means that we cannot have such a set. Okay. So by convention, in mathematics, we use capital letters to represent sets. And so in labeling sets, we usually use capital letters to do that. And when we are writing the members of a set, when we write down the members of a set, we write them in a curly bracket, right? So we enclose them in a curly bracket. We don't use the normal bracket, but we use the curly bracket, and we separate each element in there with a comma. So for example, with this set over here, that is a set of fruits, right? So this is a set of fruits. So we realize that inside we have banana, the comma. So you have our curly bracket, open a curly bracket, we have banana, then comma, then apple, then comma, then grapes, then comma, then orange, then comma, then purple, then close our curly brackets. So these are the elements that we have in the set that we have labeled as fruits. So if we let A, right? So we are letting A be the set of factors of 20. Then it means that we can write the set as we introduce the curly bracket, we open the curly bracket, then we have 1, we have 2, we have 4, we have 5, we have 10, and we have 20. All of them separated by commas. Then after we are done, then we bring we close our curly bracket. Okay. So we realize that in first example, we had orange, apple, purple, grapes, banana. All these are in the set that we are calling fruits. So these ones are said to be the members or the elements of the set. So the banana is an element of the set fruits. Orange is an element of the set fruits. The grapes is an element of the set fruits. The purple is an element of the set fruits. So they are said to be elements or members, right? So you can either call them elements or you call them the members of the set. So in the same case, you realize that in this set over here, the set of animals, we have the dog, we have the cat, and we have the bird. So all these are said to be members, or they are elements of the set. Okay, so when an element is found in a set, or when an object is found in a set, we use this notation over here, or this symbol over here, to show that the object is in that set. So over here, realize that we have banana. So banana is an element. So this symbol over here is read as this symbol over here is read as an element of. So banana is an element of the set fruits. So apple is an element of the set fruit. So if the object question is not a member, or it is not an element of the set, then in that case use this symbol over here. So realize that with this example over here, radio is not in the fruit. So we use this symbol over here to show that it is not in the set fruits. All right, so realize that we let our A be the set of factors of 20. So realize that we have 2 to be a member of the set A, 4 is a member of the set A, 7 is not. To realize that 7 is not, we use this symbol over here, is not a member of the set A. Okay. So from there, we can also talk of the number of elements in the set. When the number of elements in a set is referred to as the cardinality of the set. Right, so the cardinality of the set. So whenever you see, or whenever they ask for a cardinality of a set, then you should know that they are just asking for the number of elements in the set or the number of members in the set, and it is denoted by having these double lines around the set. So or we write n, then into brackets. So inside the brackets we write the name of the set. So an example of that, if we want to know the number of elements in the set fruits, so it is going to be n, then into brackets. So inside the brackets we have the set fruits, and which is the same as we having to bring a double line or these lines around the sets. Right, so if we have these lines around the set, it is the same thing as the cardinality, right? So it is 5. To realize that if you are to count the number of elements in this set over here, we have 1, we have 2, we have 3, we have 4, and we have 5. Right, so in this set, the set of fruits, we have 5 elements in there. So if we are also to consider the set of the number of elements in the set A, which the A is used to denote the number of elements in the set of the factors of 20, right? So the factors of 20. So realize over here we have 1, we have 2, we have 3, we have 4, we have 5, and we have 6. So the number of elements in the set A is 6. But then in mathematics, there are some sets that occurs frequently in mathematics. So some letters has been used to denote these sets. So the first that we want to talk about is the set of natural numbers. So when we talk of the set of natural numbers, there are these sets over here. So starting from 1, so we have 1, 2, 3, 4, 5, 6, 7, and so on and so forth. And it is represented by this capital N. Right? So this capital N is used to represent the set of natural numbers. And we also have the set of integers. So when we talk of integers, we are talking of the set of all positive and negative whole numbers. Right? So -5, -10, -6, 0, 2, 3, 4, 5. So all these are integers. So the set of all integers is represented by this letter Z. Then we also have the set of all rational numbers. So when we talk of rational numbers, they are numbers that can be expressed as fractions, right? Numbers that can be expressed as fractions. And they are also denoted by the letter Q. And finally, we can talk of the set of all real numbers, right? So when we talk of the set of all real numbers, we are talking of, the rational and irrational numbers, right? So it is made up of more rational and irrational numbers. So any number that you can think of, that is 2, 5, -6, the square root of 4, the square root of 6, which is an irrational number, pi, is an irrational number. So all these are contained in this set over here. That is a set of all real numbers. Okay. So there are words by which we write down sets. Usually, if the element in the set is not that huge, the cardinality of the set is, not that huge, we can just list down the element in there with comma separating them. So just like this. But then if there is a set that has a very large cardinality and it has a pattern in it. So take note, right here there is supposed to be a pattern in it. So if there is a set that is large and it has a pattern in it, then we can write the set. So for instance, let us consider this set over here, a set of all natural numbers that are greater than or equal to 1 but are less than 100, right? So greater than or equal to 1 but then they are less than 100. So if we are to list down all of these numbers, you realize that it will take a lot of time. So what we have to do is we write down some few elements in the set, then we bring our 3 dots. Alright, then we can bring our last element, which is going to be 99, because we said less than. Okay, so the last element over here is 99. So you realize that we started off by listing the elements 1, 2, 3, 4. So you realize that there is a pattern, and the pattern is for any number. For us to get to the next number, we just have to add 1. So it is 1, then 2, then 3, then 4, and 5. So there is a pattern. So in that case, we can bring this 3 dots over here in order not for us to waste our time to write down all the elements. Then bring the last element, which is going to be 99. Okay. And also, there is also another way by which we can write down sets. That is, if we decide to use the set notation form. So in that case, we have the set notation to be given as this, right? So we have x, so we have the curly bracket, then inside the curly bracket we have x is such that, then a of x. So this a of x over there, this a of x is just the property that the x will have to satisfy in order to be in this set, right? So the property to be satisfied by the x in order for it to be in the set. So an example of that is what we have over here. All right, so for example, we say b is equal to, then we open our set with the curly brackets over here, then we have x is such that, so the column sign over here is read as such that, so x is such that. So now this will now be the condition for x to satisfy in order to be in our set. So now this is the condition, this a of x. This is the condition that the x will have to satisfy in order to be in our set. So it says that 1 is less than or equal to x and less than or equal to 10, where x is an integer. So the condition is for an element to be in this set over here, it would have to be an integer which is between this 1 and 10. So just by the way the set over here has been defined, we should be able to tell the elements that we can find in there. So realize that we have 1, we have 2, we have 3, we have 4, 5, 6, 7, 8, and 9, and 10. So because of the way the set has been defined, we can tell that these are the elements that are supposed to be in there. So realize that every element in this set over here satisfies this condition. That is, first, it is between 1 and 10, and it is also an integer. Okay, so let us look at this second example. So this is a condition that x will have to satisfy in order to be in this set over here. So x is a multiple of 3 less than 18. So in order for an element to be in this set over here, it would have to be a multiple of 3, and it would also have to be less than 18. So it means that the element over there, you are supposed to have 3, then 6, then 9, then 12, then 15. If you are a multiple of 3 and you are not less than 18, so for instance, you know that a number 21 is a multiple of 3, but it is not less than 18. So it therefore means that this 21 over here cannot be in this set. And also, if you are a number and you are less than 3, sorry, you are less than 18, but then you are not a multiple of 3, you can also not be in the set. So for example, we have the number 10. 10 is less than 18, though, but then you realize that 10 is not a multiple of 3. So therefore, 10 also fails to be part of our set. Okay, so we can define the last set over here, which is the condition over here is x is a prime number which is less than 12. So inside this set over here, you will have to be a prime number, and also you have to be less than 12. So realize that we have 2, we have 3, we have 5, 7, and 11. So all these numbers over here are prime numbers, and again they are less than 12. So if you are a prime number and you are not less than 12, like the number 17, you cannot be in this set over here. And if you are a number less than 12 and you are not a prime number, so for instance 8, then you can also not be in our set. Okay, so that is what we mean by using the set notation to represent sets. So we have the x such that then the property follows. So with this example that we have been using from the beginning of the class, if we are to use the set notation to represent this set over here, then it will be written as x is such that, so then the condition will be x is a factor of 20. So just by the way it has been stated over here, then the elements in that set should be the 1, 2, 4, 5, 10, and 20, because these are the factors of 20. Now move on to the types of sets. So the type of sets, the first set I want to talk about is the finite set. So when we talk of a finite set, it's a set whose last element is known, or at least a set whose cardinality is known. So a set that we know the number of elements in a set, or a set that we know its last member, right? So this is what we mean by the finite set. Alright, so we can put a number to the number of elements in the set. So maybe we can say that the number of elements in a set is maybe 10, then 20, or 1,000, or 100, or 1 million. So we can say that these are the number of elements in a set. Then when we talk of the infinite sets, when we talk of an infinite set, it is a set whose last member or last element is not known. So we don't know what the last element will be. So in other words, we cannot tell the cardinality of this set because we don't know the number of elements in there. So for instance, if you are asked to list down the set of all natural numbers, right? So we know that the set of all natural numbers starts from 1 to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we can go on and on to the millions, to the trillions, to the billions, and yet we will not be able to find the last element of this set over here. So if we ask you for the number of elements in the set of all natural numbers, it would be impossible for you to get an answer for that because in the first place, you don't even know what the last element is supposed to be. Okay. Then the next type of set that we have to talk about is the null or the empty set. So when we talk of the null or the empty set, it is a set with no elements or no member, and it is denoted by this symbol over here or the curly brackets without anything written inside it. So it is either you are going to use this symbol over here or you are going to use the curly brackets without any member inside it. Please make sure that you don't use both of them at the same time. Make sure you don't do this, because if you do this, then you are telling a different story. Actually, this over here is a set. So what you have over here is a set that contains the empty set. Alright, the cardinality of this set over here is 1 because it contains the empty set. But then if you are really talking about the empty set or the null set, then it should be this or that. So it means that the cardinality of the empty set is supposed to be 0. But then if you do this, then you are going to get the cardinality to be 1. So please make sure that you don't do this. Okay. Then we talk of the universal set. So we are going to discuss the universal set when we start talking about the Venn diagrams. So it is just the set of all objects under discussion, right? So we will discuss it when we get to the Venn diagrams. Then we have equivalent sets. So two sets are said to be equivalent if they have the same number of elements. So take note, it says that the same number of elements. So if the two sets have the same cardinality, so for instance, consider these two sets over here, right? Consider these two sets over here. So this is the set 1, 2, 3. This is the set X, Y, Z. The cardinality of this set over here is 3. The cardinality of this set over here is also 3. So therefore, since they have the same cardinalities, then it means that these two sets over here are equivalent. Then we also have the equal sets. So two sets are said to be equal if they have the same members. So all the members in a set are the same. So an example of that would be these two sets over here. That is a set P and the set R. Right? So you realize that in a set P we have A, then we have B, and we have C. In a set R we have C, we have B, and we have A. Another thing that I need to talk about is the order or the arrangement of a set. But it doesn't matter how the set has been arranged. The most important thing is what it contains or the element in it. And so it doesn't matter how it has been arranged over here, as far as all the elements in this set P over here can also be found in this set over here, right? And again, all the elements in this set over here also can be found in this set over here. Then it means that these two sets are equal. That is, the set P is equal to the set R. So now let us talk about the subsets. Let us consider these two sets. So we have the set A, which contains the elements A, B, L, C. And we have the set B, which contains the elements C and B. Then, when we talk of subsets, this set over here, A, is a subset of, this set over here, B. The B is a subset of the set A. Because we realize that all the members of the set B are also contained in the set A. Right? So if all the elements in the set B, please take note, it says that all. So if all the elements in the set B is contained in the set A, then B is said to be a subset of A. And this is how it is denoted. So I think with our example over here, if we are to use our example over here, then it is supposed to be the B, which is rather contained in the A. Alright, so there is a little bit of a typo over here. Let me cancel this one out. Then this also will be A, so it is A, then B. Alright, so we can cancel those one out and cancel this one too out. Now this over here is supposed to be B. I am making the changes because of the diagram over there so that it would explain our diagram better for us. So this over here is also supposed to be A. So this is supposed to be B. And this is supposed to be A. Okay, so by the definition, it says that if all the members of the set B, so this one it is B, if all the elements of the set B belongs to the set A, so just like what we have in the diagram over here, so if all the elements in the set B is also in the set A, then B is said to be a subset of A, and it is written as B, then the subset sign, then A. Or you can also decide to write it as A, then use this. So right now, realize that this one we have obtained a sign. Right, so you can also represent it as that. So an example of that would be if we have the set A, which is defined as X is such that X is a multiple of 3 less than 15. So with that, we can define the A to be 3 6, 9, and 12. And then we have B, which is X is a multiple of 6 less than 15. So we have 6 and we have 12. So you realize that in this case, the B is a subset of A because all the elements in this set over here is also contained in this set over here, right? So you realize that we have 6 over here and we have 6 over here, and then we have 12 over here, and then we have 12 over here as well. Okay, so it means that the B is a subset, right? A B is a subset of A. So if we have this over here, then the B is contained in the A, and that is how it is represented. Gotcha. And again, I want to give another definition for the subset because of the power set. When we're talking of a power set, there is something in there that we will need a second definition of the subset for. So another way of defining a subset is if we have the set A and we have the set B, and we can take off some elements from the set A, and the set A and the set B will be equal, then it means that the B is a subset of A. So what I mean is, with these two sets over here, so the set A and we have the set B, if we can take off some elements from the bigger set, which is the set A, so we realize that with this we can take off A from this set over here, then we will only be left with B and C. And in the set B, we have B and C. So realize that around that we have taken out the A, the set A is equal to the set B. By the way, we defined the equal sets. So if we take off some elements from the set A, and we can have the set A to be equal to the set B, then the two sets, then we see that the set B is a subset of the set A. So you should have this definition in mind because I am going to use it later on. Okay. So now we want to look at the power set. So when we talk of the power set, we are talking of the number of subsets, right? The number of subsets in a set. That is what I mean by the power set, right? So it is the collection of subsets of a set. As well. First thing that we have to look over here is, let me talk about the B first, right? So every element or every set is a subset of itself, right? So every set in this world is a subset of itself. So remember the first definition of subset that I gave in the previous slide said that if all the elements in this set over here is also contained in this set over here, then in that case, then this set over here will be a subset of this set over here. So you realize that every element in the set over here is also in that set over there. So in that case, we have A is a subset of A. And this time around, we are using it with this sign over here. So this sign over here means that all the elements in this set over here is contained or equal to. So it is contained in it, or it is equal to all the elements in this set over here. Right? So that is why we use this symbol over here. So anytime we'll want to use the fact that every set is a subset of itself, then you have to use this subset symbol, right? Not the first one we used initially. Because this time around, you realize that all the elements in here, in fact, the two sets over there, they are equal, right? This set over here is equal to this set over here. Okay. And again, the empty set is a subset of the set A. The empty set is a subset of the set A. So what it means is, remember the second definition of the subset. So let's say we have this empty set over here. So this is an empty set, a set that doesn't contain anything. And this is the set A. It contains A, B, C. If we can take off some of the elements over here and have the two sets to be equal, then it means that this right here will now be equal to that, right? So after we have taken off all the elements in here, now this set A over here is equal to the empty set. After we have taken out all the elements in there. So, and therefore, it means that using the second definition of the subset we did in the previous slide, then the empty set is going to be a subset of A. So you have to take note that the empty set is a subset of every set in this world. And every set in this world also is a subset of itself. Okay. So now let us move on to the power set. And so when we talk about the power set, it is a collection of subsets of the set. So first, we know that the empty set is a subset of the set A, and the set A itself is also a subset. So we have the empty set, which is a subset of the set A. We have the A itself, which is a subset of itself. Then we have this. So realize that a set that contains just BA is a subset of the set A. A set that contains AC is a subset of this set over here, A. The subset which contains the element BC is a subset of this set over here, A. And again, the set that contains just A is a subset of the set A. The set that contains the element B is a subset of the set A. And the set that contains the element C is a subset of the set A. So to count the number of subsets in the set A. So all these are sets, and they are subsets of the set A. So the number of sets in here, if you are to count, we have 1, we have 2, we have 3, we have 4, we have 5, we have 6, we have 7, and we have 8. So it is 2 to the power 3. So realize that this 3 over here is the number of elements in this set A, which is 1, 2, 3. So therefore, to find the cardinality of the power set, right? If you want to find the cardinality of the power set, it is just going to be 2 to the power n. So 2 to the power n is so 2 to the power n. This is the cardinality of the power set, right? Good.